Will we have any other tests next today?
Not today. I'm almost done. I have like 5 more to grade, but Thursday for sure.
What's around that?
Average feels average. Like you guys did fine. Probably around like maybe 35 out of 50. That's kind of what I'm feeling, but I'll wait for the numbers to come in. Yeah.
That's brought us down. Yeah, I did. It's 25.
No. I don't know the average just yet. That's just what I'm feeling. I haven't graded. Yours is one of the 5 I haven't graded yet. Yeah. So I mostly looked at kind of your thought process, the exact formats I used. I'm not, and I took like maybe back in my talk for that. Okay. I can see if your thought process was right, but what's wrong. A lot of people are kind of in that.
Yeah.
So, very, very.
I know like the answer.
Yeah. No. I'm looking at your whole process. I'm not looking just at one. Yeah.
It makes it easier. You don't have to read my exam. You can put 50 on 50.
I'm not that overburdened.
Yeah, I don't want to,
I appreciate though.
Yeah. Or for like, you can put 2 out of 2 hours. It's a plan. Is it going to take that long or just?
Yes. Yeah. Just write down. Okay.
Well. Friends, no one nationals.
You're already getting a good thing for that. So this is something different.
If I don't know about that.
We'll see. We'll talk to them.
I don't think you can show it's. I didn't read the mind.
All right, it's 1 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good. After the midterm, so good to maybe hear my voice instead of taking the exam. Maybe neither is a great option, but lesser of 2 evils maybe. Speaking of the exam, I'm almost done grading the exams. I don't have them ready for you guys just yet. I have like literally 5 more to go. But Thursday for sure I will have them done. Okay. Average right now, it's hard for me to say exactly what it is without putting in the numbers in, but you guys did it feels like you guys did fine. So I think average will probably be around maybe like 35, 36 out of 50. That's kind of what I'm feeling, but we'll see what the numbers actually are. And by the way, when I say that's just the sense I got. It's not that I'm aiming for that particular number or anything like that. Yeah.
Proud of us.
Of course, I'm always proud of you guys.
Thank you.
Okay, so today we're getting back into talking about what we were talking about last Tuesday. So we were talking about convection. So I have a little bit more to talk about in terms of the non-dimensional numbers, Reynolds number, Prandtl number, Nusselt number. So we'll define all of those. And then we'll actually start to do some calculations today. And so we're going to be talking about the first, I would say, big application of your convection, which I call external convection. So we'll talk about what that means. We'll do an example today, and you'll kind of see how these kind of problems are going to go. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So this whole unit that we kind of started last Tuesday is all about convection. So, convection is something we've been using it, right? So as part of our problems up until this point, as part of the midterm problems that you guys just finished doing, we've been doing convection. The only problem is that up until this point, the whole idea of convection has been simplified for you. Okay. So up until this point, we've been doing calculations with convection. right? So the idea of convection and the concept of convection is nothing new. The only difference, the only thing up until this point is that the convection coefficient H has always been given to you. Okay. So basically, in any problem that has involved convection, H was given to you as if it were just another parameter in the problem. But that's usually not something that's easy to obtain. Okay. So what we're going to talk about this week and the next week and the next week after that and the next week after that are just, different methods for how to solve for H. Because what you're going to see is that it's really kind of situation dependent. So when we do examples and when you guys see homework 4, so homework 4 I almost have ready for you guys too. You're going to see that the problems actually look very similar to the problems that you have been doing up until this point. The only difference is that, you're not going to be given H. Okay. So I do have one example for you guys today. You're going to see it's worded almost exactly like the problems we have been doing. It's just that the H is missing, and then you're going to have to solve for it using the methods that we're going to talk about. Okay. Okay, so how do we actually go about this? So the main way that we solve for H, right? At least, the way that we can do it without simulations, because honestly, that's probably the real answer, is that you have to use computational fluid dynamics, some kind of computational heat transfer to solve for H. But if you're doing hand calculations, probably the easiest way to do that is to make use of non-dimensional numbers and their correlations. We're going to be using a lot of these kind of non-dimensional numbers. And there's really kind of 3 players, and there's kind of 3 actors on this stage. And so, we started going over them last time. Okay. The first non-dimensional number that we're going to use is the Reynolds number. Okay. So Reynolds number, we usually give it the symbol RE. Okay. So the Reynolds number is mostly used to kind of discuss or to kind of quantify the aspects of the fluid flow. Okay. So the formula for Reynolds number, RE, is given by the velocity U multiplied by L, some characteristic length, divided by the kinematic viscosity. That's typically the form that I'm going to use. And the main, well, the Reynolds number actually is going to be used in the formulas, but one of the other main things that we're going to use the Reynolds number for is to determine whether the flow is going to be laminar or turbulent. Okay. So remember, we talked last Tuesday about kind of the differences between laminar flow and turbulent flow. The thing to kind of remember is that, laminar flow is typically very well organized, typically very well behaved. The velocity streamline is going to follow a very fixed path. Whereas turbulent flow is a lot more chaotic. So there's a lot more kind of mixing. There's a lot of kind of random motion. And typically when you have turbulent flow, turbulence generally enhances your convection through convection coefficient. Okay. And what you're going to see, we're going to see kind of later today that there's going to be actually separate formulas. So there's a formula we're going to use for the convection coefficient in laminar flow, and a separate formula that we're going to use for the convection coefficient in turbulent flow. And that's kind of the trend for kind of everything that we're going to do. Okay, so determining whether a flow is laminar or turbulent, something that's really important. It's something we're going to do in almost every problem we're going to do. Okay. Okay. The second non-dimensional number that we're going to discuss, and so this is the one we went over right before we kind of finished on Tuesday, is what's called the Prandtl number. So the Prandtl number is the symbol we give that is PR. Okay. So the Prandtl number, what this does is this characterizes the behavior of the boundary layer. Okay. More specifically, there's two boundary layers that form in convection flow. There's the velocity boundary layer, which is the fluid mechanics boundary layer. There's also the thermal boundary layer as well. And so how those two boundary layers interact, that kind of interaction is kind of summarized within the Prandtl number. Okay, so Prandtl number, you're not going to use this formula all too much because usually the Prandtl number is something that you can look up in a table. But sometimes you may have to use this formula. So Prandtl number is given by the kinematic viscosity nu divided by the thermal diffusivity alpha. Okay. Okay. But again, usually the Prandtl number is tabulated, so you'll just be able to look it up directly in a table. But there are some cases, usually for compressible gases, usually for like air or nitrogen or things like that, where you may have to use this formula. But for most liquids, you can just look up the Prandtl number in the table. Okay, it's only for cases where it's usually when you have supersonic flow or something like that, that you have to use this formula. But for even subsonic air, usually Prandtl number is usually tabulated. But I want to give you the formula anyway. Okay. All right, so those are the first two. So that's kind of what we discussed last time. The third non-dimensional number we're going to use is probably the most important one. And that's called the Nusselt number. Okay. Probably the main new non-dimensional number too, because you've probably heard of Reynolds number from your fluid mechanics class. You may have heard of Prandtl number from your thermal class. This may be the first time you heard that, but Nusselt number is probably the first time that you have heard of this. Okay. Its definition actually is very similar to the Biot number. Okay. And in fact, its formula almost looks identical. Okay. The reason we call it something different is that maybe Nusselt and Biot were homies, and so it's that you get the Biot number, we can both be famous. But the reason it's different is that the Nusselt number typically refers to characteristics of the fluid flow, and that's everything that's around that. Okay? And so if you remember from the definition of Biot number was kind of a ratio of the kind of the strength of convection over the strength of conduction. Okay. Which again, was kind of the definition of our Biot number as well. And so if you actually write out the formula for Nusselt number, it looks like the following. So we have Nusselt number is equal to H times some characteristic length L divided by KF. Okay. All right. So if you look back in your notes, you can be like, wait a minute, that's exactly the formula for Biot number, right? The only difference is what we actually choose for this thermal conductivity down here, okay? So for the Biot number, we're looking at the thermal conductivity of some solid object, right? And so we were looking to determine whether the lump capacitance method was valid for that object. So when you plug in the thermal conductivity, it's of the solid, okay? For the Nusselt number, we're much more focused on the fluid. So this Kf here is specifically the thermal conductivity of the fluid that's going to be convection. Okay. So that's kind of the main difference in that, you're going to plug in a different thermal conductivity for the Nusselt number. Okay. All right. So this is really good here because, you can see here that in our formula for the Nusselt number, we have H, right? And so generally our strategy for these types of problems is going to be, first compute the Nusselt number. So I'm going to say if we can compute if we can compute the Nusselt number for a given flow situation, a given convection situation, okay. Once we have that, then if we look up the thermal conductivity of the fluids, which you can typically do, that's usually in a table somewhere, and you plug in some length, which again is usually not hard to determine, then that's going to be our path to computing H. Okay. So that right there is going to be our general strategy. So step one in the problem is, well, step one is going to be to compute the Reynolds number. Step two, maybe look up some properties. Step three, compute the Nusselt number. And then step four, compute H. Okay. So let me write that down. All right, so step one, compute, well, actually, usually before you compute the Reynolds number, you need to know the fluid properties. Right, so step one is to look up fluid properties. Okay. And usually this is going to be from some kind of table, or, now that we're in 2025, you can probably just, there's online calculators for these. Okay. Because what you're going to see is that a lot of the fluid properties that we're going to be using depend on temperature. Okay. So things like the viscosity, the density, the Prandtl number, all of these things change with temperature. So you need to look up the fluid properties for every problem. Okay. Okay. Step two is to compute the Reynolds number. Right. Which you should be able to do because you're going to have the viscosity from the problem, some kind of length from the problem. The velocity is usually given to you, and you have the viscosity from step one. Okay. Step three is to take all of your results from steps 1 and 2 and use that to compute the Nusselt number. Okay. And so what you're going to see is that there's going to be multiple formulas for the Nusselt number depending on your situation. So depending on whether you have laminar flow, turbulent flow, whether you have kind of external convection, internal convection, whether there's free convection involved, you're going to see. Okay. So step 3 here is to use the correct correlation, okay, to compute the Nusselt number. Okay. Then step 4, once we have the Nusselt number, then you're going to use that to compute the convection coefficient. All right. And so then after step 4, after step 4 is just, do the rest of the problem. So after step 4, usually you're going to be at a point where, you're going to have a problem that looks very similar to the problems we have been doing. So maybe it's a thermal circuit problem, maybe it's a heat equation type problem. So step 5 is, kind of do the rest, actually compute something from that system. Okay. I know that's very vague and not that helpful, but you're going to see it's, the kind of the variety of problems that we have been seeing, that's step 5 for you. Okay. All right. So the reason this works, kind of the linchpin in this whole process here is step 3. Okay. Because it turns out, and the reason, I've kind of introduced all of these non-dimensional numbers to you is that all of these non-dimensional numbers are very closely correlated with one another. Okay. And so what that basically means is that the Nusselt number is a function of the Reynolds number and the Prandtl number. Okay. Okay. So if you can compute the Reynolds number, if you can look up the Prandtl number in a table, there's usually a formula out there that relates those two quantities to the Nusselt number. Okay. And then once you have the Nusselt number, you can use that to compute H. Okay. So that's kind of our general game plan, at least for the next, maybe 2.5 weeks. All right. Any questions on this? Okay, good. Okay, so let's jump into the kind of the first application area, which is what I call external flow convection. Okay. So kind of the next couple of weeks here, we're going to be looking at certain kind of flow situations because depending on the nature of the flow, that's going to change. Essentially, it's going to change our Nusselt number correlation. Okay. So kind of the only way that we can really tackle this is to look at each of these kind of situations kind of individually and to kind of see, first of all, what characteristics these types of situations have. And second of all, how do we actually compute Nusselt number from these situations? Okay. Okay. So the first one that we're doing is external flow convection. So these are situations when when you have fluid flow in an external environment. And what that basically means is that the boundary layer is allowed to grow kind of unimpeded. Okay. So actually, all of the flow kind of boundary layers that we've been drawing up to this point have all been external flow convection. Okay. Okay. So canonically, it looks something like this. And so, we have some kind of flat surface, and we have flow that's coming at it. Right. So the one thing that characterizes external flow, convection is that there is a notion of the free stream. Okay. So we have free stream velocity U infinity, a free stream temperature T infinity. Okay. So oftentimes we call these the free stream conditions. Okay. And then once that fluid flow hits this plate, we're going to have a boundary layer that can start to grow. Okay. So again, this right here is the boundary layer. But you can see here that we don't have any object, we don't have any surface that's above this plate. And so this boundary layer can just keep continuing to grow. Right. And what we say is that it can grow unimpeded. Okay. So if this plate kind of continues onwards, this boundary layer will continue to grow, and that's going to affect the flow. Okay. Now, the opposite of external convection is internal convection, which is what we're going to cover next week. And so in internal convection, you have two kind of bounding surfaces, and eventually the boundary layers are going to meet. Okay. And so in that case, the boundary layer will stop growing at some point because there's just no place for it to grow anymore. But for external convection, we kind of assume that there's kind of an infinite amount of space, or semi-infinite, I guess, if you want to be kind of, specific. And this boundary can just keep growing as much as it wants to. Okay. Okay. So this right here, this is kind of a classic flow situation where we call flow over a flat plate. It's the one that we're probably going to be focusing on just exclusively for today. But of course, there are other external convection situations as well. Okay. So some other common ones, we have flow over a cylinder or flow over a blunt body. Okay. This is another one that we're going to go in detail probably on Thursday. Okay. So we have some kind of cylinder or blunt body, and we have flow that's coming, that's hitting it. Okay. And so what's unique about the blunt body is that the flow has to go around the body. It can't just go through it, right? And so you have kind of a boundary layer that kind of forms, and we have kind of a separation region or a wake region around like that. Okay, so some other ones that we probably aren't going to go in too much detail. There's literally dozens of these types of situations out there. You could have flow over a bank of tubes. Okay. So remember, if you remember when we were talking about fins, we talked about that this having a bank of fins or kind of an array of fins is something that is pretty common in practice. There's a lot of correlations and a lot of studies on that. Okay. Another very interesting case is when we have what's called an impinging jet. Okay. So this is an interesting one where you have a jet of fluid. So let's say you have like a hose or something, and it's spraying fluid at a wall. Okay. And then when the fluid hits the wall, it has to kind of split into kind of two paths like that. Okay. And so the way we describe this is we say that this jet of fluid is impinging on this wall, and then that's going to create kind of a unique flow situation there. And there's different correlations and different ways that we can talk about that as well. Okay. Any questions on this? Okay. Good. Okay, but for today, today just because it's our first time, let's focus on the flow over a flat plate. And specifically, let's start with kind of the simplest case where we have a laminar flow over a flat plate. Okay. So, I'm going to keep repeating this just because it's really important, but just remember that, the flow geometry is something that's really important when you're doing these types of problems. So, over the next couple of weeks, I'm going to be throwing a ton of formulas at you. And so I think the main challenge of these convection problems is using the correct formula for the right situation, whether you have laminar or turbulent flow, whether you have flow over a flat plate or a cylinder. Okay? Okay, so this is very, very important. So you need to use the right correlation that suits the situation. And so it's going to get confusing because a lot of these formulas are going to look very similar. So because they're all going to involve the Nusselt number in some way, they're going to all involve the Reynolds number in some way. They're all going to involve the Prandtl number in some way. And so, you know, the only thing that's really going to be different is that the coefficients are going to be slightly different in between these ones. But if you don't use the correct correlation, then you're going to end up with the wrong result. So you want to make sure you use the correct correlation that suits the situation. Okay. And the main two things you're looking for in a given situation is one is going to be the flow geometry. Okay. So you're going to see on the homework, you know, I'm explicitly going to ask you, you know, for this situation, what kind of flow geometry do we have? Do we have flow over a flat plate? Do we have, you know, flow over a cylinder, flow over a blunt body? Do we have internal flow, right? So that's kind of the first thing. Okay. The other thing that you need to be aware of is turbulence. Okay. Whether turbulence is going to be there or not, whether you're going to have a fully laminar boundary layer, a fully turbulent boundary layer, maybe a transitional boundary layer, okay? So those are kind of the two things that you're going to look for, okay? And so for this situation, for flow over a flat plate, right, our flow geometry is going to be that, okay? Whereas whether we're going to have turbulence or not, that's going to be given by this, okay? Okay. So let's talk about turbulence first before I give you the formula for the Nusselt number. Okay. Because the way that you determine turbulence is going to be different depending on the situation as well, right? So that's why I kind of say, you know, look at the flow geometry first, then based on the flow geometry, then you can determine whether it's laminar or turbulent. And then after you determine it's laminar or turbulent, then you can use the right Nusselt number correlation. Okay. So, you know, I think conceptually, you know, this convection is not too difficult. We're basically just using the same process over and over again. It's just, you know, using the right formula, I think, can be kind of confusing for people. Okay. So for external flow, specifically over a flat plate, okay, the flow is turbulent, or I should say, maybe I'll say the flow is laminar. If, okay. So the main thing you're going to be looking at for laminar versus turbulent flow for flow over a flat plate is you're going to be looking at the Reynolds number, okay? If the Reynolds number is less than 5 times 10 to the 5th power, okay? Okay. Then your flow is going to be laminar, okay? All right, so basically, you're going to look something like this. You have a flow, you have a flat plate, you have flow coming in. Okay. This flow has some free stream velocity u infinity. The plate has some length. Okay. So usually for flow over a flat plate, we're going to take the length of the plate in the flow direction. Okay. Okay. And so if the Reynolds number, and we compute it using these properties here. So if we say the Reynolds number is equal to u infinity times L, the length of the plate, divided by the kinematic viscosity. Okay. If that number that you get from that computation is less than 5 times 10 to the 5th, then you have a laminar flow. Okay. All right. Any questions on this so far? Okay, good. All right. So that's, you know, two of the most important properties there. We have the fluid velocity and we have the length. What about the viscosity, right? So this viscosity right here is a property of the fluid. Okay. The difficult thing with the viscosity as well as the density and the Prandtl number is that these properties are very temperature dependent. So the exact value So the exact value of this parameter will depend on what temperature your fluid is going to be, okay? So this is not something that, you can look up once and just use that for every problem. The value for these properties are going to be different for every problem because the temperatures are most likely going to be different, okay? Okay. So that makes sense, right? And so in fact, let me give you, I believe these are the properties for water. Yeah. All right, so just to kind of give you a sense of how much these properties vary, let me give you these properties for water. All right, so you have a table here. So this is not too different from, the tables that you would look up, if you have the textbook, or you can look up these tables online, okay? So if you have the temperature in degrees C, so here we have the viscosity. Okay. These are kinematic viscosities, so it's going to be meters squared per second, okay? And so what you're going to see is that as the temperature of the fluid goes up, so we go from 0 degrees to 5 degrees to 10 degrees, 20 degrees, 30 degrees, 40 degrees. And we'll go up one more, we'll go 50 degrees, okay? You're going to see that we have a very big variation of the viscosity here. So at 0 degrees, basically freezing, we have a viscosity of 1.787. Okay. At 5 degrees, so even just a small difference from 0 degrees to 5 degrees, we have a pretty big difference in the viscosity here. So about a 15% difference. So this becomes 1.519. Okay. At 10 degrees, this becomes 1.307. At 20 degrees, this becomes 1.004. At 30 degrees, this becomes 0.801. Okay. 0.658. At 50 degrees, we have 0.553. Okay. Okay. So you can see we have a pretty big difference. And so it's not like this is a huge, well, it kind of is pretty big, but it's not an abnormally large temperature gradient either, right? So when we go from 0 degrees, and if we heat the fluid up to 50 degrees, you can see that viscosity kind of reduces by a factor of 3. And so, which is kind of a big deal. And so that's a difference between your Reynolds number being, maybe 1 times 10 to the 5th to 3 times 10 to the 5th, depending on the value of the viscosity, okay? So even for water, so water is kind of a very common fluid. You're going to see it a lot in these types of problems. We have a huge variation in the viscosity, okay, depending on the temperature. Right. So that's something you need to be kind of careful about when you're doing these problems is that, a lot of these properties do depend on the temperature, okay? So that includes viscosity, that includes thermal conductivity, that includes the Prandtl number, that includes the density, okay? Basically, any material property of the fluid itself, you need to make sure that you evaluate it at the right temperature. Okay. Any questions on this so far? Okay, good. All right, but then now the question is, what temperature do you evaluate these properties at? Because it's not always going to be obvious. And it gets even more complicated when you have, when you have heat transfer that's occurring, which is, what we have here, right? Because oftentimes when you have heat transfer occurring, you have some kind of temperature difference. So there's a difference in temperature between the free stream temperature of the fluid and the surface temperature of the solid. All right, so if I were to draw kind of our kind of our typical situation, right? Oops. So we have our plate here, right? The plate may be of some temperature Ts, okay? And we have fluid coming in. The fluid is at some temperature T infinity, okay? Usually Ts and T infinity are going to be different from each other. If they're not different, then we don't have any heat transfer. Then we're not really doing heat transfer anymore, right? Okay. Right. That's kind of the whole. That's kind of the whole point of this whole unit is when we have different temperatures between the fluid and the surface, right? Otherwise, right. And what's even more complicated is that, remember, we have a boundary layer that's forming as well. Remember, that boundary layer is kind of that transition region between the conditions at the surface and conditions in the free stream fluid, okay? And so with all these different temperatures and all these different transition regions going on, what temperature do we even use to evaluate these properties? Okay. So of course, the naive thing would be in this situation is, let's just take the average, right? So let's take the average with Ts and T infinity. Okay. So if we take Ts plus T infinity divided by 2. Okay. So in other words, we get kind of an in-between temperature between the surface and the free stream. Okay. And so in this case, luckily, that is actually exactly what we do. So this average between these two is often called TF, okay, which TF stands for what's called the film temperature. Okay. Right, it's kind of another way to say kind of what's the average temperature within the boundary layer, okay? And so when you come up to a convection problem, computing the film temperature is something that you're probably going to be doing most of the time, okay? Because what's unique about the film temperature, that this is what you're going to be using to compute the fluid properties. Okay, so you want to make sure that you compute the film temperature and use that one to evaluate the properties. Otherwise, your answer is going to be very, very different if you don't compute the film temperature. Okay. All right. Any questions on this? Yeah.
Pretty general assumption of the temperature.
It is. Yeah. So in reality, because you have a lot of variation temperature across the boundary layer, probably the better way to do it is to kind of see exactly what the variation looks like in the boundary layer and then get a more appropriate average from there. But even that, even just taking average is something that's not always going to work out really well too. So, for a lot of times, you're probably going to have to use simulations and computers to do this, but exactly. But this is kind of it's a pretty decent approximation for if you're doing calculations by hand. Any other questions? Okay, so with all that in mind, right? So, we've done a lot of prep work, and so I've kind of been, teasing this formula for a while. But now, after you know the Reynolds number, after you know the fluid properties, right? The last thing to do is just compute the Nusselt number. Okay, so the Nusselt number for laminar flow over flat plate is given by the following. So we have, and it's kind of a strange looking formula if you're kind of used to some of the other formulas you've seen in other classes. There's actual decimals here, which is kind of interesting. So 0.664 multiplied by the Reynolds number raised to the 1/2 power. Okay, so that's the square root of the Reynolds number multiplied by the Prandtl number for the flow raised to the 1/3 power. Okay. So for all the buildup that we've been kind of doing today, 50 minutes of buildup, this formula here is fairly straightforward. Okay. Okay, so let's finally kind of use this in an example. And I think that might be one of the last things that we can do today is that example. So, okay, so let's actually see how this is used. Okay. Okay, so let's say that we have a very hot air that's being blown over a flat plate. Okay. So we'll say this air is at T infinity equals to 300 degrees C. Okay, so extremely hot. Okay, so this might be the air inside your air fryer or something. Okay. And so let's say that this air is flowing over a flat plate that is about 0.5 meters long. And let's give you the velocity too. So the velocity we'll say is 10 meters per second. Okay, so let's go ahead and draw this. So let's say we have our flat plate. Okay, we have air that's flowing at it. Okay, we know the free stream conditions from the problems. We know that T infinity is 300 degrees C. Okay, and we know that U infinity, the free stream velocity, is 10 meters per second. Okay. All right. We know the length of the plate. We know the plate is going to be 0.5 meters long. Okay. And let's say we have a situation where this plate is being heated by the fluid. Okay. So this really is kind of inside a convection oven or an air fryer. And let's say this is the hot air that's going to cook your food. Okay. So let's say that the surface, let's say if the surface temperature is, let's say the surface temperature is 27 degrees C. Okay. So in other words, what we're saying is that TS here is 27 degrees Celsius. Okay. Right. So based on these numbers, let's compute how much the air, or the rate at which the air is heating up the plate per unit length of the plate. So that's the objective of this problem, is we want to compute the heating rate, basically. Okay. Okay. So fairly straightforward problem. So this is one we could have done previously, right? So this problem should not be too exotic. And so the only difference now is that, we're not given the convection coefficient. And so we're going to need to find that through our Newton number correlation. Okay. Okay. Because normally, if we were given this problem, say I gave you this problem maybe a couple weeks ago, you can use Newton's law of cooling to solve this problem. Right. So since we're looking for a heating rate, okay. Okay, because that's what we're looking for in the problem. We know heating rate is given by Q. Okay. I know, what we are looking for is heating per length, but we can at least form the formula for this, because this is just simply Newton's law of cooling. Which is a formula that we've used, maybe a dozen times already in this class, right? So Newton's law of cooling is Q is equal to H times A times the difference in temperature. Now, in this case, our fluid temperature is hotter than our surface temperature. And so we can say that this is equal to Q times H times, or Q is equal to H times A times T infinity minus T at the surface TS. Okay. And so, of course, we can rearrange this, right? So we know in terms of, in this case, we have a square plate. And so the area in this case is just going to be the length times the width. Okay. We're not given the width in this problem. And so, what the problem is asking for is a heating rate per unit length. So let's just divide out the one dimension that we don't know. Okay. So we don't know this. So this is not given. So let's just divide by it in the problem. So if we divide by it, we have Q divided by W, okay, it's equal to H times L times T infinity minus T S. Okay. Okay. So that's our solution right there. So that's what's going to give us our heating rate. Okay. The only problem is that in this problem, we don't know what the convection coefficient is. So H is unknown right now. Okay. H is unknown, but we should be able to solve for it because this is a flow geometry that we recognize. So H is unknown, but we can compute it based on our Nusselt correlation. Okay. Okay, good. All right, so let's kind of start with that. Okay. So for flow over flat plate, of a flat plate, we do have a Nusselt correlation for this. It's the only Nusselt correlation that we know. Okay. We know that the Nusselt number is equal to 0.664 times the Reynolds number raised to the 1/2 power times the Prandtl number raised to the 1/3 power. Okay. And of course, the Nusselt number is equal to H times L divided by the thermal conductivity of the fluid. Okay. And so, of course, if we can compute the Nusselt number, then we can compute H. And if we can compute H, we can plug into that formula above to ultimately solve this problem. Okay. But of course, in order to compute the Nusselt correlation, we have to compute the Reynolds number and we have to compute the Prandtl number. Okay. So let's compute these or look these up for this problem. Okay. Okay. So let's start with the Reynolds number. So we know the Reynolds number is equal to U infinity times L divided by the kinematic viscosity. Okay. Okay. So we have U infinity. We know U infinity from the problem is 10 meters per second. We know the length of the plate in the flow direction that's given to us in the problem as 1/2 meter, 0.5. The only thing that's missing here is the viscosity, which we need to look up for this flow. Okay. So you can look this up in a table, or if you're in front of a computer, I think the easier way to do this is to use an online calculator. So those online calculators kind of have these tables kind of built in. You just kind of give it a temperature, and it spits out your fluid properties. Okay. I have one linked from the Canvas site. If it's not there, then just kind of remind me. I'll link it again. That website might have been taken down actually, so I might need to put a new one. But there's a lot of these out there. Okay. Okay, but of course, to look up fluid properties, we need to know the film temperature. Okay. So let's go ahead and compute that first, because there is actually quite a big difference in this problem, right? So remember, the film temperature is simply just the average between the surface temperature and the free stream temperature. Okay. So that's T infinity plus Ts divided by 2. Okay. Okay. So T infinity in this case is 300 degrees C. The surface temperature in this case is 27 degrees C. So we take the average between those, we get 163.5 degrees Celsius. Okay. And so if we look up the properties of air at this temperature, okay. You may have to convert this this temperature to Kelvin. It's because usually for gases, the tables are written in Kelvin. Okay. So remember, to go from degrees Celsius to Kelvin, you just add 273. Okay. So this is equal to 436.5 Kelvin. Okay. Okay. So Kelvin is equal to degrees C plus 273. Okay. Technically, it's like 273.15, but 273 is usually sufficient. Okay. And so if you're going to look this up in the textbook, if you happen to have the textbook on hand, this is table A4. Okay. So it's one of the tables in the back, and so you're going to have to go to the back of the textbook. It's in one of the appendices. Okay. So in this table, what you're going to find out is you're going to have three numbers here that you're going to look up. So first is going to be the Prandtl number. Okay. The Prandtl number at 163.5 degrees Celsius is 0.687, okay, for air. The thermal conductivity of the fluid is 36.4 times 10 minus 3 watts per meter Kelvin. Okay. Okay. And the kinematic viscosity is 5.21 times 10 to the minus 4 meter square per second. Okay. Okay. Good. So once you have the film temperature, you're going to look up all these properties in the table, and they'll be just like that. Okay. One small note, just for this problem in particular, just because it's, actually normally for air, it's actually very hard for air to be laminar. Most time air is actually quite turbulent. For this particular problem, we're actually evaluating these properties at a much lower pressure. Okay. So this viscosity here is actually the viscosity of air at only 6 kilopascal. And that's absolute pressure, 6 kilopascal. So this is very, very low pressurized air. It turns out viscosity also not only depends on temperature, but depends on pressure as well. Okay. For most problems, you're not going to have to deal with this, because for most problems, we're going to be dealing with kind of very reasonable pressures. But in order to get this problem to be laminar, I don't know. I made these notes like 7 years ago, and I was being weird. I don't know. But in order to get this problem to be laminar, we had to evaluate them at lower pressures. And so what that does is that actually increases the viscosity. Okay. But normally you won't have to consider pressures. Just this problem is just kind of unique. Okay? So that was that. So, that pressure of 6 kilopascals was kind of given to you in the original problem, but, I didn't want to clutter it at the time. So just be aware that, when you look up these numbers, just take kind of whatever's in the table. For this particular problem, if you look up this example in the lecture notes, you'll see that there's an additional adjustment for the viscosity based on the pressure. Basically, we're increasing it by a factor of 2. But normally you won't have to do that. Okay. Anyway, so with all that in mind, we have everything we need to compute the Reynolds number. Okay. So the Reynolds number, remember, is U infinity times L time divided by the viscosity. Okay. So let's go ahead and plug in for that. And so if we plug in for that, our U infinity is 10 meters per second. Our length here is 0.5 meters. Okay. And our viscosity, once we adjust for the pressure, is 5.21 times 10 to the minus 4 meters square per second. Okay. So we do all that. We plug this into a calculator. We get a Reynolds number of 9,567. Okay. Okay. Dimensionless, of course, because, remember, all these non-dimensional numbers are dimensionless. Okay. And since this number, 9,567, this is less than the turbulence threshold. Okay. So this is less than 5 times 10 to the 5th. Then we know our flow is laminar. Okay. Which is great because we wouldn't know how to deal with it otherwise. Okay. Okay. So now that we've computed the Reynolds number, we've confirmed that the flow is indeed laminar. Let's compute the Nusselt number. Okay. So for this particular geometry for laminar flow, we know our Nusselt number is 0.664 multiplied by 9,567, which is the Reynolds number, raised to the 1/2 power. Okay. Multiplied by the Prandtl number. The Prandtl number is something that we looked up in the table, right? We know the Prandtl number is 0.687. Okay. And we're going to raise that to the 1/3 power. Okay. Okay. So we punch all these numbers into the calculator. We get a Nusselt number of 57.4. Okay. Now that we have the Nusselt number, we can use that to compute H. Okay, because we know the Nusselt number, its definition is that's equal to H times L divided by KF. Right? And so if we rearrange this formula here, we have H is equal to Nusselt number times KF divided by L. Okay. So just multiply both sides by the thermal conductivity of the fluid, divide by the length. Okay. We know everything in here because the Nusselt number we just computed. We know the Nusselt number is 57.4. Thermal conductivity of the fluid, we looked that up in a table. That's 36.4 times 10 to the minus 3. Okay. And the length of the plate is still the same. It's 0.5 meters. Okay. Right. All right, we punch all those things into a calculator. We get a convection coefficient of 4.18 watts per meter squared Kelvin. Okay. Now that we have H, we can now go back and solve this problem, as if it were before. So we did all this extra work to get to the point where we have the convection coefficient, okay? Now we can do the rest of the problem, which, for the rest of the problem, we just have one step right here, which is this Q over W formula, okay? So finally, plug in to Newton's law of cooling. Okay. We have Q over W is equal to H times L times the difference in temperature. Okay. Right, so that's the heating rate per unit width of the plate. Let's plug in all of our numbers here. So we know H is 4.18 watts per meter squared Kelvin. Okay. We know the length of the plate is 0.5 meters. And the difference in temperature here, we have 300 degrees C minus 27 degrees C. Okay. We plug all that in, we get 570 watts per meter. Okay. Any questions on this example before we wrap it up for today? Yeah.
Or when you computed the Reynolds letter, when you got 9,557.
Yep.
You said that it's less than 5 times 10 to the fifth, meaning that it's laminate.
Yes.
So you put this only for air or?
It's true for any fluid, as long as the fluid is above a flat plate. So this 5 times 10 to the fifth is specific to this geometry, but if you have a different like water or honey or something like that, then the same threshold still applies. Yeah.
Thank you.
Okay. All right, and so we'll stop here for today. And so when we come back on Thursday, we'll talk about turbulent flow, and we'll see how that changes our Newton correlation. And then we have some more examples for you guys as well. Okay. So thank you guys for coming today. I'll have your midterms ready by Thursday. If all goes according to plan, I should have your grades on Canvas by tonight. I'm probably going to try to do that before I go home for today. But I'll pass out the exams on Thursday. Okay. So thank you guys for coming today. Is that
Even her grades? Yes, it is.
everyone's? Yeah. All right. So thank you guys for coming today. I hope you have a good rest of your day, and I will see you on Thursday. Yeah. Well, so this one's unique because I didn't give you the width, and so in this case, I could just divide by W. But normally you just.
Okay, so it's okay to just like leave.
Yeah, so this problem is they asked for the heating per unit width, and so that's kind of what it is. Yeah. So well, I think I might have said per unit, but I meant per width. Yeah. Oh, good. Yeah, almost done. Yours is one of the few I haven't graded yet because I left it in my office. So so probably tonight. You'll find out.
Okay, no worries. You don't even have to have that one. I gotta see how much they are. What did you say the average was I want?
I don't know the exact one, but you guys did fine. Average usually probably 35. Yeah.
That was like 35%.
Oh, no. How's the wedding?
Good. Oh, it was so good. It was beautiful.
Nice.
I don't think I've cried.
Oh, yeah, that's usually thing for that, especially for family, like your siblings, it's like
Yeah,
it hits you.
And like during the ceremony, talking about like